let's get started with our class today. So welcome back from our break. Last week, I hope you have been able to get started on the visualization assignment. It's quite late already. We really have to move on with the class. And your assignment 1 is due by Monday next week. So I think quite a lot of good questions on various hiccups in setting this up and working on it. I hope all is resolved now. But if not, just feel free to ask in this class. Just maybe I wait for about 1-2 minutes right now if there are any questions on setting up your system for visualization and all that. Because once you have your Docker running on your laptop or your computer, you should be able to do the other experiments that are coming already. And today I actually want to start on the Spark data analytics framework. So just wait for about a minute or two to see if you have any questions or any challenges on this. Okay, if no questions, then let's start discussing about Apache Spark. And basically Lab 2 is divided into two sections. One portion is the visualization and the second portion is the analytics portion. And this is actually kind of tying together the sequence of Lab 1, 2, and 3 is something like this. In Lab 1, you learn how to connect up sort of computing nodes together, focusing more on the hardware and the networking side. How do you just link up nodes together so that hardware-wise they can talk to each other by Ethernet through your router, through your switch, and then you can then install this kind of cluster management software on the nodes. But that one, the focus is on just putting things together to let you see that you can actually assemble multiple CPUs, multiple computers together. And I think, if not mistaken, Dr. Azlan is still using the Raspberry Pi, but the Raspberry Pi is just a CPU. Lab 2 is actually focusing on the other end of the spectrum, where you are looking at if you're needing to run a data analytics, the data science workload, and then after you do the processing on the data, you want to display the results for people to ingest, for decisions to be made. Lab 2 is covering the aspect, and Lab 3 is looking at the intermediate. Let's say you have all these hardware connected and you have this high performance data analytics and visualization that you want to do. How do you pull together the resources? Basically, it is using virtual container management software, Dockerization. How do you actually spin off multiple copies of the same app? How do you scale it up, scale it down? So that will be cluster management. That will be in Lab 3. So we have spent the last couple of weeks looking at visualization with R. More specifically is to get you started familiar with using the software platform, to writing the code, to actually displaying different visualization. You've seen from 2 weeks ago how to actually access data from the CSV file and all that. You can expand on that to kind of look at other file types. The most common is maybe the JSON files and the XML files, but they're just a little bit more different, the format, but there's still a text format, just like CSV. CSV stands for comma separated values. So today we're going to be starting on Spark, and I hope that you had time since early January. I mentioned to you to start reading chapter 2 of this mining massive data sets and just browse this learning with Apache Spark, because today we're going to start touching on Apache Spark. Okay, what is Apache Spark and where does it come from and why are we interested in it? The computing revolution, basically, you can think about it from the late 1970s to 1980s. what we call the complex instruction set computer, the CIS computers become very popular. These are basically your Intel microprocessors that's pretty much in all the laptops and desktops that you have today, and even on some of the server. And the way you write program from C, C++ is called control flow programming. It's called control flow programming. Why is it called control flow? Because you execute the instructions in sequence 1, 1, 1, 1, 1. So if you have if instructions, if else instructions, for loops, while, these are all examples of control flow programming, because there is what they call one thread of execution. The program, the computer is actually executing one series, one sequence of instruction. Because there's one thread of control, and you're saying do item number 1 on this data, then you do item number 2, do item number 3, do step number 4. So step 1, step 2, step 3, step 4, all is done in sequence. The microprocessor doesn't skip steps. Then later on, maybe you learn in computer architecture that actually to speed it up, some tricks have been played in the last 20 years. They actually silently allow you to execute instructions out of order, out of sequence. And they can only do this under special condition that the instruction is not dependent on the previous instruction. But this is basically the control flow mode of programming, where the bottleneck is actually computation. That the idea is that it's very expensive to make additions, multiplications, all this logical operation. Starting about 20 years ago, this has no longer been the bottleneck. The bottleneck is it's actually now on, we have too much data, because as I was sharing with you from the beginning of the class, there's now big data, because there's proliferation of sensors, proliferation of cheap internet and fast connectivity, wireless connectivity, cheap storage, and compute is now not the problem. The problem is actually transferring the data. The problem is actually how can you actually get the data fast enough to the processors, because these processors now are very, very cheap. Your Intel processor is still very expensive because you've got like 12 cores on it, right? So there are actually 12 processors that you're buying, right? That's what your 12-core machine means. It's just that those 12 processors are grouped together, allowed to function simultaneously, like for 4 cores, 6 cores, 12 cores, this kind of thing. But you can see about it, like the price is still the same. One Intel chip is still roughly the same as one Intel chip over 5 or 10 years ago, except that now one Intel chip has 12, and then 5, 10 years ago it had only 1 or 2, right? So price of processor has dropped. What this means is that the control flow programming actually is falling out of favor lah. Why? Because control flow programming, you need to operate on the data one by one by one. Whereas what we have, the problem now is we have so much data, but we want to perform the same kind of analysis on the data. So for example, we can take our COVID-19 data set that was very cleverly suggested by someone earlier this semester. If you got data for whole of Malaysia, and this COVID data set is actually considered tiny, it's not even big or medium, it's actually tiny. If you're in the megabytes, this is really tiny. You can actually code all this in standard Python, standard C++. You don't need Apache Spark. But I want to illustrate the concept, so I'm using a small file that you can actually open and visualize separately lah. But in many industries nowadays, like airline industries, for example, banking industry, your data set range in the terabytes to petabytes. So terabyte is starting to be the size of one hard drive. The total database of many of these large companies, you talk about Netflix, you talk about Amazon, even like Shopee, all these platforms, you cannot fit all the data into one hard drive. So if you cannot even fit it into one hard drive, how do you expect to process all that data in your memory? Right? Because remember, the CPU, the way the CPU works is a load store architecture. In order for you to do a calculation on the CPU, you will learn this in computer architecture. You need to fetch the data from memory, put it in the cache. It will go from the cache. Then from the cache, it will go into the register of the CPU. And there are only like 10, 20 registers in the CPU, maybe up to 100, not more than that. So you have to actually put into that little box called a register in the CPU compute, the CPU push it back to cache push it back into memory, right? So you have to bring it into the CPU, out the CPU, in the CPU, out the CPU, like that. That's how it works. So you can't really push all of that. And if it can't even fit into main memory is roughly on the order of 4 gigabytes, the smallest nowadays, to about 200, 512 gigabytes, right? But your hard drive is terabytes. And if I tell you your data cannot even fit into one hard drive, you need tens of hard drives, tens of thousands of hard drives. So you start to have a problem because control flow obviously does not work. You can't load the entire data into memory. So you have to kind of figure out a scheme. How do I access the data from hard drive directly, or at least be able to access it in a way that it doesn't, it can actually make it seem like the data is in memory fast enough. So that's where Hadoop came in about, I think about 15 years ago. This is called the map-reduce programming model. And this is the way of programming that Google had pioneered. This is what underpins most of Google's systems. And the open source version of the MapReduce is actually called Hadoop. Open source meaning the code, everything all is shared. This is it's a Java implementation. It's called Apache Hadoop. It's now become an Apache project. Okay, and the idea behind this, what allows us to really handle all this data, is this simple idea. It is that for all this data, you don't really have a complex set of processing. It's not like column 1 or column 2 of this data, you want to do one type of processing, then column 3, you want to do another type of processing. It's more like you have like billions or thousands or billions of rows or columns of data, but you want to do more or less the same set of tasks for each data element. So this is what sometimes you may have heard older terminology in computer architecture called single instruction multiple data. This is a very fine granularity, but here the idea is that I actually want to do the same type of processing on all the data, right? So the level of complexity of my instructions is not very high because I probably don't have that many instructions that I want to do. But I need to repeat it over and over and over again on a huge data set that cannot even fit into main memory, that cannot even fit into one hard drive, but I need to repeat it over and over again. And here's where it gets very interesting. If you do it that way, then the intelligence here is to say that rather than I just do it one instruction, I process all the data, then I do a second instruction, then I process all the data, third instruction, I process all the data. So let's say I've got 4 instructions, right? I want to add all the data elements in one column. Then I want to repeat it for all the columns, right? And then after I add, I want to multiply by a certain factor. Then I want to take the square root. Then I want to kind of display it. So let me 3 steps, right? It's 3 instructions, but I need to do it on billions or thousands or billions of columns. So if you do the control flow way of programming, you would actually just do a for loop. You say, I do instruction 1 first, but I take instruction 1 for all the 10,000s or billions of data elements. After you finish, only I do instruction 2. I do it for all the thousands or billions of columns that I have for instruction 2. After I finish, I do it in instruction 3. Right? So this is how control flow programming works. It will execute one instruction first, do it for the entire data set. Only after finish, it will go to the next instruction because it's going instruction by instruction. This is control flow programming. This is what you typically call structured programming in UTP, your C++ with your function and all that. Okay. But the problem with that, there are 2 problems. The first problem is, if I need to do all this, I need to load all the data into this, then I'm going to spend a lot of time. Let's say I have tens of billions of data elements. My memory can only fit 1 million. So I need to fit 1 million. I do that processing. I shift the 1 million data points out. Then I fit another 1 billion. I do the processing. I shift the 1 billion data points out. So it's a little bit challenging because I don't know how to break up this operation because I need the results from instruction 1 to do instruction 2. But I cannot actually store the intermediate results from instruction 1 in my memory. I have to push it back to the hard drive. So you have to actually shuffling data in and out, in and out, in and out, right? So it takes a long time, right? That's the first problem, right? The second problem is if in the middle of instruction 1, the power goes out, or if in the middle of instruction 1, one of the hard drive fail, or one of the memory get corrupted. You probably have not seen this because maybe you've not worked with computers long enough, or you've just got one system. But in a data center, it happens quite frequently. Sometimes happens, if for a large data center, it could happen as frequent as once a day. Something will break down. All your computation wasted, throw away, throw in the garbage. You have spent all that energy, you've spent all that time, and you can't reuse any of the computation because it just vanished, right? Something broke down and then you don't know how to retrieve, right? So this is the problem of control flow programming. Number one, you actually have to do all the analysis of one instruction on all the data first, and sometimes that takes a lot of time. And then if there is any kind of error or fault, hard for you to recover. You have to restart the instruction from scratch. This is not good, lah. Okay. Data flow programming, MapReduce, Hadoop, use a different approach. And the approach is something like this. It's saying that I actually need to do instruction 1, instruction 2, instruction 3. I need to do it on all the data. But is there a way that I can break the data up into small chunks? Okay. So now rather than breaking up the execution by instructions, that means I execute instruction 1 first, then I execute instruction 2 first, then I execute instruction 3 first. That's what the control flow programming is doing. I break up the operation by data. That means I said the first, not even if I got 10 billion rows that I need to work on, I take the first 10 rows. I said this first 10 rows, I process it on one CPU. The next 10 rows, I process it on a second CPU. The third 10 rows, I process it on a third CPU. I'm running the same instructions. Instruction 1, instruction 2, instruction 3. I said that I'm now doing it in a local fashion. A small chunk of data is going into CPU 1. So that data, because it's only maybe 10 rows or 10,000 rows or 10 million rows, the whole data can fit into memory. I can compute, I can save all my intermediate results into memory. So it's very fast. I don't have to shift this data in and out. I just shift it, this small amount of data, boom, into processor 1. It will compute instruction 1, 2, 3, 4 straight away. But it only computed on one small part of the data. And then I have another CPU that will compute for the next 10,000 rows, for example. Instruction 1, 2, 3, 4 on these 10,000 rows on a small part of the data. Then I've got a third CPU to do the same. And you can see where this is going. The way this programming model works is I'm breaking up the data and sending these smaller chunks of data into many CPUs. And I do it in such a way that all the data can actually fit into memory. All the intermediate results can actually fit into memory so that I don't spend all this time shuffling data in and out of my hard drive. I just send it once into the CPU. There's a small amount of data processed. It processes very fast. And then I've got the intermediate results. This, in MapReduce or Hadoop terminologies, is called the mapping operation. The mapping operation is nothing else but you got a set of instructions, you got a set of data analysis instructions that you want to execute on the entire large data set. The map process is basically you break up your large data into small chunks. Each of these small chunks will go into one processing unit. Whether that processing unit is a thread, a separate CPU, a separate core, it doesn't really matter. It's just one separate processing unit, and this separate processing unit will execute instruction 1, instruction 2, instruction 4 on that small part of the data. But then we come to one problem of this. If it was so easy to break this up, now I could do it to control flow, right? The problem is it's not that easy to do this, right? Because after you calculate the results from instruction from core 1 and core 2, you must find a way to combine all that. Because if I want to take the mean of all 10,000 rows, and then I'm breaking it up into, all 10 billion rows, I'm breaking it down into rows of 10,000. I've only got the mean of the first 10,000, the mean of the second 10,000, the mean of the third 10,000. But actually what I want is I want the mean of the whole 10 billion. But the way I've broken it up in data flow is I've broken it up into the mean of 10,000, 10,000, 10,000, 10,000. So there has to be another step where I collect all the intermediate results from all these small processing cores and I combine them. This is called the reduce step. And let's say I take a simple example from the mean. If my job is to compute the mean on 10 billion rows, I will first put 10,000 rows in the first CPU, 10,000 rows in the second CPU, 10,000 rows in the third CPU, 10,000 rows in the fourth CPU, until I have 1,000 CPUs with 10,000 rows. So I got 1,000 means, but they are means only on a small portion of the data. So that's the mapping operation. The reduce operation then becomes two of these cores will send their intermediate results. The intermediate result here is the mean value of the 10,000 to another core. And this core will then take the average of that. So if I take the average of two 10,000 rows, I have the average of 20,000. So then I can reduce my 10,000, the mean of 10,000 rows. They suddenly become 500 means of 20,000 rows. Then they become 250 means of 40,000 rows. So you can see the reduce operation is also using this same idea. I can have smaller instructions. I'm sending the intermediate data. Now it's not from my hard drive or my storage. They're coming from the processing of intermediate CPUs. And gradually they combine. Finally, I'm able to compute the total mean of 10,000 rows. Okay, how does this solve the two problems that we talked about just a few minutes ago? The first is A, because I'm ensuring that the amount of data that is going into one CPU is not so large. In fact, for Spark, it is designed so that the data will fit entirely into memory. That's the big difference between Spark and Hadoop. Spark and Hadoop are actually doing the same thing. They're doing the map reduce operation. The idea is to break up the data so that it can reside into one location, that it can reside into one CPU. Hadoop, the data is residing locally in one drive where the PC has fast access to that drive. Spark, the data is made even smaller and it must be fit into the main memory. And this is how Spark can achieve 1, 2, or 3 orders of magnitude, between 10 to 1,000 times faster processing time than Hadoop. Right? This is the main advantage of Spark. And this is why Spark is called in-memory analytics. In-memory analytics, because it is ensuring that the small chunk of data fits into main memory. Therefore, you only pay the disk access time once. So if you learn computer architecture later, you will know that there are certain order of magnitude. If you're accessing in cache, let's say you're accessing one data element in cache, it takes roughly about 1 nanosecond to get one bit or 1 byte from cache, one access. If you're accessing from main memory, from RAM, it's somewhere order of like 10 to 20, 30 nanoseconds. If you're accessing it from hard drive, it would take several tens of milliseconds. So at least 1,000 times slower if you're accessing it from hard drive. So this is how Spark is faster than Hadoop. Okay, Hadoop and the Hadoop Distributed File System, HDFS. So coming back to that idea, how does this solve the first two problems? The first problem is now because I'm only ensuring that the data is small enough that it fits into main memory. The computation is very fast. Okay, and then what I'm trading off is I'm able to now split this computation into many compute units. So if I have actually happen to suddenly, all of a sudden, if I suddenly able to add more cores, double the amount of cores, can I speed up this computation? Yes, I can. I can break my data instead of 10,000 rows. Each CPU have 5,000 rows. So do you think you will compute faster? Of course you will compute faster because you're working on a smaller data set, you're transferring a smaller data set. But you cannot arbitrarily keep increasing this because there is an overhead time to manage all these CPUs in parallel. As you keep breaking up more, the map step will become shorter, and ultimately you'll be dominated by the time it takes for you to transfer that small amount of data to how many map operations. But the reduced time will take longer because if you got more individual units, it'll take longer for you to combine the results. So there is a trade-off there. And the chapter 2 here is giving you that analysis, those formulas, is deriving the analysis for 3 use cases: word counting, dense matrix multiplication, and database join operations. Is giving you how to analyze the trade-off between splitting up data into many units and reduction so that you can estimate what is the speed improvement or what is the speed degradation. That's why this mining a massive data sets chapter 2, that chapter is meant to teach you this thing, okay, to walk you through that process and give you some back of the envelope calculation so you can figure out how to split this up into map tasks, how to put it down into reduced tasks. So I've just explained to you how problem number 1 from control flow is circumvented. Is because we are not making one compute unit kind of access the hard drive so many times for, or maybe many of the hard drives, because 10,000 10 billion data points, if it exceeds 1 terabyte, 2 terabyte, if it's petabyte domain, you cannot store in one hard drive. So instead of having one CPU, you can have many. Each of them are working on a small amount of data. The trouble is your network has to be very fast and very high bandwidth lah. And that's why the emphasis now is on networking, because networking is actually the bottleneck lah today, the transfer of data. And you can see by solving problem 1, somehow we are able to inject parallel computing into this whole process. Why? What is parallel computing? Parallel computing is like multiple computers sharing the workload. How are they sharing? Each one is computing the small task, the small map task on their small chunk of data. And then later they will share their data again and they will compute the reduced tasks, right? So if you have more processors, you can split the job up easily by breaking up the data, not by breaking up the instructions. Traditionally, for control flow programming, if you talk about the older style parallel programming, people have to break up the instructions, and that's very tedious, very time consuming. It needs a lot of expertise. You have heard about mutex, locks, semaphores. These are all fine-grained parallelism, how you are trying to find ways to break up the sequence of instructions so that you can parallelize. Data flow programming, the way I've explained it to you, this can be done automatically by Hadoop, by the MapReduce software. It can be done automatically by Spark. If you want to suddenly break up this same task among 10,000 CPUs or 100,000 CPUs or 1,000 CPUs, the exact same code can be run on 10,000, 100,000, 1, 2, 5 CPUs. Any number, you just have to tell Spark, I want to split this data up to how many chunks. That's it. It's just one change, one line change. This is not the same for control flow. Control flow, you have to go in, you have to kind of change the loops, recompile the program and all that. So data flow programming actually simplifies the parallelization process on the assumption you are doing analytics on data, you're not writing it back to the drive. Okay, and so this is good for things like, let's say, web service and all that kind of stuff. But if you've got a lot of fine transactions like banking and all that, maybe that's a little bit hard. This data flow programming, Apache Spark, is for analytics. It's like you've got lots of data, you want to get a big picture, you want to get analysis on that. This is great for this type of application. How does it solve the second problem, which I told you, if something suddenly breaks down, there is loss of electricity, hard drive failure, how does it solve this problem? Okay. Remember that we are computing on one small chunk of data, one CPU. So let's say you have a power failure. It's not likely your power failure will affect all your 10,000 CPUs, because most likely those 10,000 CPUs are spread across different data center, different physical location. That's why you have Amazon Cloud. That's why you have Google Cloud. That's why you have Microsoft Azure, right? Because they have data centers, they're pulling all these CPUs. If one data center goes down, like let's say very unlucky, got earthquake or got typhoon, the whole thing shut down, no power. Yeah, you lose all the compute units there, but you have another one. Or if there's a local failure on the hard drive, that hard drive only affects one server, but you've got 10,000, that got like another 9,999 servers that are still running. What means is, instead of you losing the results from all like 10,000 different compute, you lose the result maybe from one or two of these computes. The remaining 9,998 units, they already computed their intermediate result. They can proceed with the reduced operation, while Spark or Hadoop will restart the computation on the two failed units. Okay, so I repeat that. Because you've broken up these tasks into small chunks, each chunk, okay, not the instructions. The instructions are the same for each of the processor, but they're only operating on a small chunk of data. The remaining data that has been computed on and all that, you can proceed with the reduced operation. So the computation is still proceeding. You are not really delayed too much. Your delay is only on restarting the computation on the failed unit. And since that computation is small, I mean, the number of instructions is the same, but the operations are the same. But because you're operating on a small amount of data, you can restart it quickly. It will only add a small amount of latency or small amount of delay to your final result. Because in the worst case, all the other results are doing their reduced operation already. They've reduced up to the final number, only waiting for the map operation of these two failed units to work on. Then these two failed units, once they work on, they do the quickly reduced operation, it will be done. So data flow programming, the MapReduce model, also greatly enhances fault tolerance and fault recovery. Why? The fault tolerance is if one of those units or two of those units fails, the rest of the results are still valid, and they're still proceeding with their computation. So it's tolerant to the faults lah. Unlike instruction in the control flow programming, if one memory fails or something like that, the whole thing goes down. You have to restart everything. So it's not fault tolerant. You have to restart the work. You lose all the work. For data flow map reduced programming, you don't lose all of it. You just lose for that small unit, and you can restart that unit. That means its fault recovery is quite simple. And what it typically does, it doesn't just restart that unit for using one unit. If you've got some free CPUs, it will restart that same unit. It will replicate the results into multiple units. And the fastest one that finish will send the result, and then you just kill the computation on the rest. Okay, so these are two examples, two key features of why it's good for us to study the map-reduced programming model, which you are going to be programming. And it's not difficult. The key idea is just the key value pairs and how you break up the data. It's not difficult, but it needs a little bit of mental rewiring lah. You have to approach things in a different way lah. And you have to understand that the way of programming is called map reduce. This is the concept. It was pioneered by Google. The open source implementation is Hadoop, Apache Hadoop, and Apache Spark. In this class, we are using Apache Spark because I want to do the computation in memory. It's just faster. Okay, so at this point, any questions before we now go down to the hands-on? Just give me some feedback. Did you follow that? Anything that was not clear? You had read this chapter 2 and you wanted to ask some questions. So I'm just happy to just kind of interact with you a little bit to see how this works. How are you? Okay. Okay, can you give me a bit of feedback? Just type something or turn on your mic. Do you hear me?
Yes, still okay.
Still okay.
Yeah.
Okay, all right, thank you. Okay, thank you for this one. All right. Okay, great. Then we just jump straight in lah. I will share with you these example files lah. Okay, this is how Apache Spark looks like lah. Okay, and let me just open up my PowerPoint to kind of describe the concept to you lah. And what I'm doing is I'm going to open up. I'm going to start doing some processing on a CSV file. And this CSV file is vex_booster_combos lah. Basically, I'm looking at the vaccination, the data on vaccination in booster vaccination in Malaysia lah, because it's kind of interesting. So this is a CSV file. It's kind of small, 1.9 megabyte. It's not big data lah, but it looks something like this. I have the actual date, okay, and then I've got the state, the district, and these are all just the combination lah. Presumably this is AstraZeneca. I don't know what C lah. I don't know what C. I think Pfizer is this one. PPP, triple Pfizer, Sinovac. So it will actually list down here the number of people getting that combination. Okay. So if you look at this data, it's got how many rows? 25,121 rows. Okay, and it's a comma separated value, right? So once in your life, you should actually just open it up without Excel lah. So you just open it up. I think you have to click open with. Is shift right click, open with Notepad. Right, this is actually what a comma separated file actually looks like. Right, you at the low level, it's basically text encoding, comma, 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 comma. Every time there's a comma, Excel will interpret it as another column. But basically, it's just this is how it looks like. It's just a fill a row, commas, 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 then carriage return. This is what a CSV file looks like. You should also try to explore to see what a JSON file looks like, what's an XML file looks like, because these are all text file formats. You can actually open them up and read them directly. So we want to do some processing on this, and I want to do it in the Apache Spark way, right? So maybe, for example, I want to find out a simple question like, which combination of booster, vaccine and booster is not done in Malaysia, right? So if it's not done in Malaysia, it just means that the sum of all these rows is going to be 0. You agree with me, right? Because it's telling me on each day at each location, which is the booster combination that was given. So I can find out things like which is the most popular booster combination, which is the least popular, which is not implemented in Malaysia, or what is the popularity by the region, by the district. I can also find out things like in which district I want to track at the district level. Let's say Kinta is where we are at. If we want to see what is the progress of the vaccination, I can do all these kind of things. Okay, so we're going to be trying to look at Apache Spark to figure this out. So this file, in order to read this file into Apache Spark, this is the command. This is actually the list of commands actually is listed in this book. I give you this book as a guideline. It's on your uLearn. You start looking at chapter 3 and chapter 4. The loading part is actually in chapter 5, but this one has more stuff but you can actually just look at text files and comma saturated files and JSON. These three are actually the most basic ones. You can just look at that without doing all this advanced stuff. So it's just loading and saving your data. You can look at this a little bit, but that's not the key part. The really focus is you have to look at it on chapter 3 and chapter 4. And RDD stands for redundant resilient distributed data set. RDD is just the fancy word in Spark for that small portion of the data that has been moved into one unit. Remember, we talked about large data set. I'm breaking up the data elements in that large data set. I'm putting a small chunk into CPU number 1, a small chunk into the memory of CPU number 2. Each chunk of that data in Spark term is called RDD. Okay, so an RDD is the basic chunk of data. So what this is doing is actually splitting up this file into small chunks of data. Each chunk of data is going into one compute unit, whether that is 1 processor, 2 processor, 3 processor. That one can be set up later. Okay, so how specifically is this data being split up? When you do this command, SC means Spark context. That's just saying the Spark engine. Text file means you're reading this text file at this location. We've covered this location. I'm using this lab 2. This is mounted to my Zeppelin. I've showed that to you in the previous lab session. So when you're reading this automatically takes this file and breaks it up into small chunks. How are the chunks broken up? If you use SC text file, the chunk is broken up by lines. So this first line will go into one memory location. This second line will go into, so not one memory, one CPU. This another will be another CPU. The third will be another compute unit. Okay, I'm now going to change to compute unit. I'm not going to say CPU because what happens is Spark will break this out into many primary compute units. Then you look at how many physical CPUs you have that you say you want to work on. So it will break it down to maybe 10,000 or a million compute units. But then if you only have 3 CPUs, it will manage. It will maybe put 1 or 2 of these elements, compute unit, onto one processor. Then after it's done, it will shift it out into memory, then push back in again, back and forth. So Spark will manage that. But here what I'm trying to say is that the data now, this whole data with this command is broken up into basic elements of line by line. Okay. If you have a text file, let's say you have a book or you have a log file that you want to go through, the Spark will actually break it up as word by word. A single word will actually be one data unit. Okay, so these lines here is basically that data structure that is actually representing those units, those small data groups, each RDD. Okay, so I'm going to use the term RDD. So lines here is basically an RDD. Each element of the RDD is a line in this CSV file. You follow me so far?
Yes, sir.
Okay, if you don't, you have to speak out. There's no shame in this because these are very new concepts lah. I would say I'm not sure how many universities in Malaysia are teaching this at the moment lah. Maybe at the more advanced level they're doing it. So this is, I think, even in industry, if you go to very serious data science groups only, you'll be starting to learn Spark or even to work on that. But that's not been very popular yet because it's not that easy lah. But actually, I tell you, it's quite easy, right? Okay, this book will give you 3 different ways of writing Spark commands. Spark is a computational framework. How do I explain this? Spark is like a framework. Uh, okay, let me see how I can explain this. If you've ever used like OpenCV, like a machine vision library like OpenCV, or if you've ever used, okay, let's think about it like that lah. The best analogy I have is something like this lah. Everybody, I guess you're all are using TikTok nowadays, right? No more Facebook, right? Facebook is like old-fashioned for people like me. You're using TikTok nowadays, I guess, and all those video things lah. Okay, so TikTok is a platform, right? The platform is compatible on Apple, it's compatible on Android, it's compatible with maybe your web browser, it's compatible with even Linux, right? You can actually go on the browser on Linux and check it, right? So Spark is a little bit like the TikTok app lah, right? It's fundamentally there. How you interact with Spark, how you give commands. Apple platform will be different, Android platform will be different because they have fundamentally underlying different processor, different operating system lah. So here, Spark is the framework, is like the TikTok, but how I actually give Spark command, I can give the commands in Python language, I can give commands in Scala language, or I can give commands in Java language. It's doing the same thing. It's just the syntax is different. You are using a different sort of intermediate software to communicate with the Spark framework lah. Okay, so it's the same like TikTok. You're using a different device with a different app operating system to communicate with the same app, right? It's the same TikTok, right? And then there's it does the same things, right? So this book will actually give you 3 versions. I am using the Scala version. I'll give all my example in the Scala version because I have problems setting up the Python version. It just doesn't work. It's crazy. I don't know how to debug it lah. No time to debug it, right? Otherwise, Python would be kind of nice because you can actually link Python with, you can actually do your visualization and other things in Python, right? But I'm using the Scala version. If you like Java, you can use Java, but Java is a little bit more low level and a bit picky. So I'm using the Scala version, and val means this RDD is a constant variable, VAL, right? That means once you declare it, you cannot change lines already. You can only just take data out of the lines. If you declare var, then you can actually put one RDD into lines. Then you can actually later on in the computation, you can assign another set of RDD into lines. Okay, so that's the main difference. But it's actually very simple. You just declare either a value, which is a constant variable, constant data element, or a variable. Okay, and this is actually creating an RDD. Each RDD is actually a line in this. Okay, and Spark operations, there are basically 2 types lah. One is called transformations, and one is called actions. Okay, transformation is just you are kind of doing some manipulation on the data so that you're presenting it into different type of RDD. Okay, so I'll give you an example of what a transformation could be. I may have all of these data, right? So now my RDD is just one line, one line, one line, one line. So they're individual lines with all this data. But let's say for my processing, I'm not interested in AstraZeneca. I'm just interested with only the Pfizer vaccines. So I actually just want to throw out all of these. I want the date, the district, the state, and Pfizer vaccines. So I can actually perform a transformation operation in such a way. I will drop all of these non-Pfizer vaccine data from my RDD. I create a new RDD, which is just date, state, district, and all the Pfizer combinations, and I throw away. So that's one example of a transformation. I can create a new RDD, this one. So I'm sort of modifying my data to make it a little bit different. Or for example, I actually just want to get the district and the number of Pfizer triple Pfizer, for example. I don't need the state, I don't need to know the date. So I can do what is known as a key value. The key is actually the district name, and the value is actually the number of Pfizer, triple Pfizer booster, right? So I can reshape my data in such a way that it will simplify my computation later, right? So the way I do this is I will restructure my RDD. I will add, reduce elements, or it could be very interesting. Also, instead of taking this raw data, I want to create a new RDD where at each time and district, I'm going to add up all the Pfizer version. I mean, I'm going to take the sum of this, and then I just call this one Pfizer, at least one Pfizer, at least one AstraZeneca. So I just add all of these, and then I create a new data element. So this is an example of also a transformation. I'm transforming my RDD into another type of RDD that can prepare it for other things. So we can, the RDD operations, the transformations is listed here. So one example of transformation is you can do filtering, right? Filtering is things like, let's say I only want the data for Perak. So basically I will only retain in my RDD all those lines that has the state Perak. I can do that. That's an example of transformation. But the key idea here is transformation. It is allowing you to modify your RDD so that you have the data that you want to process. The next set of operation is called the actions. The actions is where you actually do your data analytics. Okay, so that transformation instructions is more of you are preparing the individual RDD, you are kind of formatting, you're kind of rearranging, you're kind of adding, subtracting data so that you can better control the type of RDD, its size and all that goes into each processing element. Actions is where you do the map operation and the reduce operation. And remember, the map operation is basically you are given an instruction for each RDD, each element in the RDD, each like data group in the RDD. What is that set of instructions I need to do? That's a map operation. The reduce operation is basically I'm going to take the results of the map operation from each programming element, combine it to get one final result. So actions is where the map reduce evaluation is done. Okay, so at this point, do you have any doubts on the transformation type of operations and actions? We've not gone into detail yet, but I just want you to get the concept first that there are some kinds of operations in Spark that is meant to just modify or reshape the RDD. And then there's the actual data analytics operations, which are the actions type operation. Do you follow that concept?
Yes.
Okay, great. So if you were to scroll down to this is the list of all the transformation operations that you can perform on RDD. So this gives you an example. If your RDD contains 1, 2, 3, 3 lah. So in this case, each data element is if your RDD contains this lah, that means one data element is this. If you perform a map operation, you're basically adding 1 to all these data elements. Your new RDD will have this programming element, right? So this, let's say it's just one data element, but you got maybe 10,000 or 10 million of these, right? So what's going to happen is it's just showing you the example of one of these. After you do this map operation, you will get this. So the syntax is the name of the RDD here. So in our case, the name of the RDD is lines. So when you have this sc.txt file, this is your RDD. This represents all the data in chunks of that data element. So you put lines.map. It doesn't really matter what variable you put here. As long as you just put something, you can put any name here, doesn't matter. But what this means is that whatever element in that RDD, you will transform it to this. That means this X represents all these elements here. And the transformation that needs to happen is you add 1 to all of these. Okay. And here is adding a function lah. You are actually adding a you're actually operating a function on this X lah. So you can go through all of these, and you have transformations that are only operating on single data elements of the RDD, and you have transformations that are operating on pairs of RDD, pairs of data from the RDD. So single element meaning it will take just one data element here, one row here, and it will do the transformation on all of these. Pairs means it will take all possible two pairs here, either from the same RDD or through different RDD, and you will perform this operation like intersection, subtraction, and all that. Okay, so these are example of the transformations. So look at page 38 lah. These are all the simple examples, and the actions are listed. The actions is the data processing part. They are listed here lah. You can count the number of elements. You can count by value. You can order them. That means you can sort them. You can reduce them, meaning that you're combining them, you're taking them and you're summing them, aggregating them, and all that. Okay, so this is the two main reference pages because all your coding will just be using the functions from 38, page 38, and the functions from page 41 and 42. That's really it. That's all you actually kind of need to really work on this. The rest all is just explanation, and the key value pairs we'll cover next time. There's a third set of transformations specifically for key value pair computations. But for today, I just want to cover the transformations and the actions and introduce you to these functions. Okay, so what we're going to do, first, I want to know how many data elements are here. Of course, I can check. Because this my file is small. I can just scroll all the way. I look at the last row, 25121. So there are 25121 rows, but actually there's only 25120 because the first row is only this, right? So if I want to calculate how many rows, I can basically use Apache Spark to do this right? So I break this up into RDDs. Each RDD is a line. And then I perform an action on the RDD. I'm counting the number of data elements in the RDD. So I can run this. Okay, so you see I have 25121 data elements, right? So the data elements, as I told you, are the rows. So it's matching, right? Then if you want to take a look at what the first row looks like, the first data element, you can actually just use the command first. That's also an action. Okay. So this is what it looks like. Date, state, district, this is that data element. Okay, but it's not so interesting here. Now here's where it gets a little bit more interesting. This is where the data analytics part comes in. You see, so in order to count like this, you see, it's just a one-line command. Now, what if I apply a transformation? What if I ask you, I want to know how many data rows there are for 2021, only the year 2021. So what I can do is I can filter the lines so that I perform a filter operation so that each line, I only retain the line that contains the word 2021. And then I count how many lines there are. I can do that. So let me do that. So there are 19,154 entries for 2021, meaning that in this whole data set, 19,154 rows have the date 2021 and everything else is 2022. You see, I can just calculate that just with this one line of code. I didn't have to do anything. Why? Because this is just the way it works. I'm not breaking it up by loops. For loops is a control flow method. This is a data flow method. I'm breaking it up by data elements. Okay. So if I want to find out how many entries in Kinta district, I can just put Kinta district here. So I got 160 entries in Kinta district, right? So this is an example of how I've used a transformation to reduce my RDD to be something that only I want to do, and then I want to process, and then I just perform an action on this. Okay. So you have any questions about the counting process?
No question.
Okay. All right. So this is illustrating the most basic operations for transformation. I'm just filtering and counting. Okay. So this is how I can do the count. And for example, if, for example, I just want to take all the data elements that have Kinta, right? So this RDD, this generates a new RDD. I'm looking at it, this is what my data element looks like. So if I do this, I can get rid of the first row lah, which is not very useful lah, which is this one here lah. Okay. Now, I can also do something very interesting. I can actually create an RDD where I can actually split up all the data elements here into zeros, into all their individual elements. So if I run this command, line.split by this, what this is doing is, this is actually splitting up. So the RDD lines is actually split up by lines. Each data element is lines. If I run this operation, this flat map operation, and then I split each line further by the comma, going to get individual words or characters. Okay, so here this RDD is basically splitting it up by each text string before the comma is one separate data element. Okay, is one separate data element. So for here, what I want to do is, if I want to use this, I can actually use this operation to actually tell me how many measurements were taken in the district of Kinta, how many days they are measuring that lah, or I can check at individual. I can just count the number of words where Kinta appears lah, or I want to say how many measurements are taken in the date of maybe 2nd of September 2021. So I can split all of this up, then I just literally will count the number of dates here lah. I can do that lah. But here what I'm saying is that you can further restructure your RDD so that you can actually split it up so that it becomes individual elements here lah, right? So these are sort of the basic operations you can do to juggle things around. And here, if I want to calculate how many entries there are here, if I do a count, this is what it will tell me lah. There are 678,267 sort of individual entries. That means 678,267 columns in this particular, not columns lah, tabs lah, tabs in this particular file, this RDD. So I can reshape it that way. Okay, so here is further another way to do it. I'm actually showing you another way to kind of play around with this. First, I have my line RDDs, and I only filter it in such a way I get only those RDDs containing the para state. That means I'm only looking at data in para state. Okay. Then after I filter up to get the data in para state, I'm splitting this up by commas, okay? And I'm taking only the second element, right, in the row. So I split it up by commas. I'm taking the zeroth location. The first, I'm only taking the second element. So here, this part here, what I'm doing is I'm actually creating an RDD with only the district names in it. And then I double check that that's what my RDD. I look at what the string is. The string is Bagan Datuk lah, which is basically one of the districts here in Perak lah. Then if I were to change it to Kedah, I can actually just extract the districts of Kedah. So this sort of operations here that I'm showing you, just giving you an idea of how to use the different transformations to reshape your RDD so you can do more interesting things. Okay. When I want to start counting, okay, this is an example of a reduce operation. Here I'm taking array number 20 lah. So number 20 would be 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I want to check the number of people that have taken Pfizer Sinovac booster. I only want to pay attention to this row. So the way I do that is I first filter only those lines or those measurements in the Kinta district. Okay, I split the line so that I can access each of these elements separately, and I only take the entryth in the 20th row, which is the PPS one, and then I convert that text string into an integer to integer. Okay, so this from this part onwards is giving me an RDD with only elements in PPS row, that's the 20th row. That means the index starts from 0 all the way to 20th. Only the 20th row, but for Kinta district only, right? So this is giving me that. And then I take pairs of these, I add them up, because this operation will tell me how many total people or doses for Pfizer Sinovac was given to people in Kinta district only for all the time. And if you want to check only for 2021 or you want to check only for January 2022, you can do another filter operation here, okay, where you first find Kinta, then you also sort only by date. You can actually have another that you sort by date. So for the whole data set, 594, I have 594 people in Kinta Valley taking PPS Sinovac, PPS kind of booster. If I further do a filter, I just want to know those people in Kinta Valley only in, let's say, December of 2021. I can actually filter by 2021 here like that, because the date format, we check the date format. The date format is like this. So this will tell me all those only in December 2021. Oh, sorry, this line contains, okay, that's why I gave you the, oh, okay, this is the format 2021-12. Okay, so for the month of December 2021, only 112 people in the Kinta district had Pfizer Sinovac booster and the vaccination. Okay, right. So I'm going to share this file with you. Basically, I put it up on uLearn, and then you just take, this is the Zeppelin file. You just dump it into your mount point in your local directory, and you can open this up, and you can test this out. Okay, and I will be giving you your first Spark assignment in the next couple of days. Okay, it will be using this transformation and action. I'll get you to start performing some analytics. Maybe we will look at some of the interesting data sets, and you can try to think how to frame it in a Spark operation, write the code, and get the result for me. And I think you can see where this is building up to. We will do maybe one on this, then one with the key value pairs, and then we will combine all the concepts. You will generate all of these analytics, and then you will send it to display on the visualization, and that will complete the class for lab 2. Is that okay?
Yes.
Okay, so that's all I have to share for today. Yes, go ahead.
Sir, I got a question.
Yeah.
Regarding for the R language and Spark.
Yeah.
Okay, for example, you are using filter, right? Filter function.
Yeah.
So in Spark, it's acceptable because there's a library in it. But why R language don't have? And I found out that R language, most of the library is not exist. Is it because only in Zeppelin book does not have, or is it why I don't get it? Why R Zeppelin don't have a lot of language?
Okay. Okay, good question, Roy. You are exploring. Okay, let me explain it this way. Okay. You are used to thinking about programming as languages, but I'm trying to now shift your thought to frameworks. Okay, frameworks, from languages to framework. Language is just like the API, how you actually interact with the framework. But you are used to thinking of it as this kind of black box. I just call everything, and because many of you grow up in an environment where the apps are so perfect, because like one Facebook or one TikTok apps, there are like thousands of engineers working to make it good, so a lot of it is hidden from you. You don't realize that at the end of it, every single line, how this executes, somebody had to write the function to actually implement it. Okay, so R itself, the programming language, or Spark itself, there's a whole collection of instructions and functions underneath of that. right? So it's not fair to say Spark has this instruction, R doesn't have. It doesn't compare that way, lah, Roy. That's why I was spending the time today to actually explain to you Spark is not a language. Spark is a framework. It's a fundamentally different way of writing programs. So you cannot compare Spark with R. R is a different language. It's also a framework. It's actually more like a language, R. Why? Because the strength of R is it gives you libraries that can perform statistical comparison, and it doesn't actually, it tries to hide a lot of the statistical computation from you. Okay, so R, the benefit is it's giving you results, function, statistical results, right? You're performing statistical operations. You're performing mean. You can do all kind of fancy statistical algorithms. In Spark, there is no library for statistical operations. You are writing a program to actually code those statistical operations from scratch. You have to make it up from basic additions, subtractions, and all that. Okay, so the filter and all these are data manipulation sort of operations. The reason that R and Spark, R doesn't have the filter like Spark has, or if it has, is actually done differently. It's because it's done different, because R is basically a control flow program. If I want to do this sorting, for example, the line contains para, the way R will have to do it is R will have to actually open up the data, then it will go through, check the first line, is it there? Check the second line, is it there? Check the third line, is it there? Check the fourth line, is it there? Check the fifth line, is it there? Then you have to open a new memory, and then you have to actually copy this one by one. It's control flow programming. R uses control flow programming. That's why it's difficult or tedious to write this kind of sorting functions in R. It can be done. Good programmers can do it. I can do it. I think some of you also, if you think hard about it, you can do it. It's very tedious. Spark, the reason you've got this one-line filter is because the way of programming Spark, the way it works, is fundamentally different from R. It's fundamentally different from Python. It's fundamentally different from C, C++. It is a data flow programming model, not a control flow programming model. It's a different way of writing programs. Okay, so that's what I'm trying to break. That's why this session today is really important, because it's coming as probably a little bit of a shock to all of you, lah. I suppose, lah, because there are like 4 major programming approaches in the world today, lah. One is structured programming. You've only learned one, I believe, which is actually you're doing if else. The second is actually object-oriented programming, where you actually declare objects. Each object actually has a function in it, and so you have to instantiate objects. The third is actually visual programming. This is basically your Simulink, your LabVIEW, where your function blocks are actually you're connecting blocks together. And the fourth is actually this data flow programming. There are sort of others, like Scala is also functional programming and all that, but I'm not going to that. But the 4 major useful sort of ways of programming, this is what I've observed. So you've only probably have a lot of exposure only to one. Some of you maybe have done Java or C++. You have some exposure into the second, the object-oriented. The third one, I mentioned the Simulink, the MATLAB one. Actually, that one is actually called event-driven programming. And if you've done Microsoft Visual C++, or you've done GUI programming on a Windows system, it's all event-driven programming. That means your program calls is not in sequence. You call the functions when there's an activity that triggers it, like a button click and all that. So there are actually different models of programming. And here I'm actually taking you a different model. It's a data flow programming model. This is why Spark filter command doesn't exist in R, because it is approaching this totally in a different way, Roy. Okay. Now, you're probably also unhappy why, R, a lot of the libraries are not present in Zeppelin. Like I said, Zeppelin is not a programming environment. It is a tool that allows you to write code and link to the compiler. When you talk about programming, if you think about, let's go through, you think about what a programming is, right? At the end of the day, your CPU is executing assembly instructions, add, shift, and all that. Okay, so when you write a program, let's say in C, C++ program, what you're trying to do is you're trying to convert your C, C++ syntax into a sequence of assembly commands. That's what happens at the microprocessor. The problem nowadays is there's so much of stuff in between that in EE, we can't actually teach you all the way to assembly level already. I don't know if you've ever actually seen or done an assembly programming. It's really, really painful. But the assembly programming is nice in the sense that actually every assembly command can be translated into its binary version. So you actually can literally generate the entire binary string that the processor will see. That is what needs to be generated to run a command on your processor. What happens is you write in a high-level language like C, the compiler will convert that into assembly commands and binary commands for you. That's what a compiler does. Okay, so the compiler will do that. The linker or the loader is actually loading other commands. Let's say you are using a function call from the math.lib library or standard lib.h library. Do standard lib and math.h library, the instructions to perform addition or that already has been coded into assembly already. So when you write your code calling those libraries, what you're doing is you're actually giving the reference to that function, and the compiler and the linker will combine these two together so that that sequence of binary instruction is sent to your CPU. It's not magic. This is just what's happening at the downside. This is why we have libraries, because libraries are nothing else but a declaration of all the binary instructions that have to go to the CPU to execute a floating point instructions, for instance. Or if you want to do a compare, or if you actually want to take the mean, or you want to, sometimes you just call this function, you don't think about it. But these functions, the reason you can call that is because somebody else has written the low-level implementation in binary for that. And what you're doing when you're calling this library is you're just saying, when the compiler compiles my code, the compiler will automatically say, okay, call this function. The compiler will just say, at this point when I have to execute this function, I will just go to the instructions in my library. There's the binary instructions. I run those instructions, and then I go back to your function. That's how the processor does it. Okay, why am I telling all this? Because I'm trying to put you the link or what it means when you're adding a library, right? So at your point, when you're adding the library, you actually need to know where is all these instructions, low-level instructions stored lah. So this is why you need to install this library into R, because R, when you install R, it doesn't come with all of these. It only comes with a few standard ones. If you want to use others, you have to actually save it in. Now, that is for C, C++. Compilers and linkers are for fairly low level, C, C++, Java. If you're talking about Python, you're talking about R, you're talking about MATLAB, it's actually even more complicated than that. It doesn't compile. It has a translator. There's another layer that sits between the compiler and your MATLAB code, and that is the engine or the translator. So what actually happens is when you write your MATLAB code, when you write your Python code, when you write your R code, that R code is converted into what is called an intermediate instruction, intermediate representation. And that intermediate representation has one-to-one mapping with the with the binary compiler. And the reason you do that is because if you run on an Apple, in the old days, Apple was actually running on Motorola instruction set, and then Windows was actually running on Intel instruction set. The processor has totally different instruction set. That means the binary codes to do addition are totally different. So when you compile a program in C++ and Java, you have to compile for Intel. You have to compile for Kirin processor. You have to compile for ARM processor. All processor different. So you have to separately compile, meaning that C++ code, in order for me to run on my Kirin processor, or in order to run on my ARM processor, I have to recompile. I have to regenerate that binary. Where MATLAB, R, Python does is they transform this to an intermediate representation. So it's like a virtual compiler. And that intermediate representation, there's another library that does the instantaneous translation. So you can only write the code once. You don't need to compile, but in real time, depending on the system that is running, it will do a translation. You say this intermediate representation is equivalent to this instruction in Intel. This is equivalent to this instruction in Kirin. It's equivalent to this instruction in ARM. So R, Python, MATLAB, these are translated languages. You can run them on different platforms because they have a two-step process. Compilation is still done, but compilation not to the binary code of the processor. It is to the intermediate instruction. And then there's another library that does the real-time translation to the binary code of the processor. Okay, so this is why R is sort of fundamentally different lah. R is not doing MapReduce. R is just giving you a set of functions that can compute statistics and all this well. Now, why Zeppelin is not a programming language at all. Now I'm getting to why I mentioned all this to you, because fundamentally you need a compiler, you need a linker, a loader, right? This is actually to combine it into the binary of that particular processor. If you're using Python and MATLAB, you need the translation engine. That's why you have to install Python framework. Python framework is nothing else but the translation engine that will convert your Python code into intermediate representation. And then that intermediate representation, there's another step that it will convert it directly in real time to the processor instructions. So MATLAB is a translation engine. R has a translation engine. Python has a translation engine. That's why you can write these codes one by one and you will execute. Actually, it's doing the compilation, everything all when you click the enter button, it's doing the compilation all in real time. That's why it's working. Okay, that's how it's working, why it's working. Okay, so Zeppelin, Microsoft Visual C, Borland IDE, Eclipse, these are called IDE, Integrated Design Development Environment. They have nothing to do with the compilation. They're just giving you a nice screen where you can type the code, and then I have nice colors that can give me, and then if there are errors, it just helps me to flag. They're just visualization tools that help you to write the code better, right? So Zeppelin is not a compiler. Zeppelin is not a translator. It is just a nice fancy screen that I can write my code, and when I click this plus button, what does Zeppelin do? Zeppelin will send this code to the Spark translator. That's it. Okay, so Zeppelin is not a compiler. It is not a translator. It's an integrated development environment, right? Just like Eclipse, just like Borland C++, just like your Microsoft Visual C. Except that Microsoft Visual Studio is a little bit more complicated because it's not just an integrated development environment. It also gives you libraries, functions that you can run and do things on the Windows operating system. Okay, so Zeppelin, again, is not a compiler. It's not an interpreter. That's why you have this thing called interpreter, because Zeppelin is just a front end that give you a nice box to type the code. If you don't have Zeppelin, you have to type the code in the notepad like this, you know. That's how we used to do it in the old days, right? You have to type it here, or you go to Linux, the terminal line, you will just open a text file, you type the code, and then you call the command, the compiler by command line. That's GCC. GCC is a command line compiler. All right. So Zeppelin is just pretty lah, right? So when you say that why the libraries are not there, it's not because it's not in Zeppelin, it's because this particular virtual container, I wanted to make the setup easy for all of you, because if you want to actually go and use the lab, can, but you know, you have to make the trip to the lab and all that kind of things lah, and then that reduces the amount of time you have to play around with this. So what I was trying to explain in the past tutorial is that when we do this, that container, that Docker container that seems so easy, you just write the line and it's on, is because it comes with pre-installed R libraries already. And what we are seeing is that that container is not that well set up. When you want to install additional R libraries there, we have problems. The key problem is the compiler system is not set up in that container, right? So then when your R library, what your R library is doing is it's trying to pull all this code, this existing code that is what you call your library, is trying to save it locally into the container. And there are some of these libraries that it doesn't get the direct binary translation. If it saves the binary translation, you have no problem, you can install this library. But some of these libraries, they have defined it in such a way that it will bring in the high level R code, and your local machine will actually have to do the compilation to convert that R code to binary. So that is what's failing when we try to install the R libraries in Zeppelin. That's why I'm saying that to solve that problem, that takes a lot of time lah. And for now, I think you can do without quite a lot of the visualization, because the goal is not for you to make the prettiest visualization, it's for you to get a handle, able to get some visualization out and show and do interesting things with what you're able to do. So I know maybe you're feeling a little bit disappointed with that, but if you really are very interested to pursue the visualization, then you install RStudio on your laptop. You just write the code in RStudio, it's okay. In RStudio on your laptop, you don't have to use Docker. You can actually use all those visualization. And that's how we done it in the previous versions of Lab 2 lah, that we separate the visualization. But the reason I'm trying to put this into Zeppelin now is I want to show you that whatever analytics you generate from Spark, you can feed it into the R visualization directly. I want to close the loop for you to let you see that visualization analytics does not need to be separate activities. They're actually an integrated activity, right? But what makes that challenging is you have to choose your proper platform, your framework. You know, are you doing Python with Node.js? Are you doing Python with Python? Are you doing Python with R? Are you doing scale up the the link of the back end and front end, there's just so many choices. And for teaching reasons, I have to make a decision to choose one. So Zeppelin is the trade-off. It's not perfect in all ways, but it's got some strengths. And one of the main strengths, actually, the reason I chose Zeppelin is to show you this, is that among some of you, or maybe in a later version, is if you all can take it, not maybe your batch, but in a future batch, you will see that Zeppelin actually can host JavaScript and HTML code. So you can literally go into this window, you type HTML, you type dynamic HTML, you can display the web service here, right? That is where I wanted to actually kind of highlight. This is the main reason why I chose Zeppelin, is because it can show you how you can integrate both the back-end computation. Apache Spark is what I've chosen for this, but Zeppelin can also run Python. So if you want to do your data analytics in Python, it's also okay. You are not going to be using MapReduce. You're not going to be using this kind of map and filter function, but you can use the standard for loops, if loop, control loop. Nothing wrong with that. It's just that when your data becomes big, you are going to have a little bit of problem, but you're not going to get big data in this course because your systems just can't take it. So if you look at Angular display using front-end API, if you go to usage here and you go to the tutorial, this is actually giving you instructions how to program the AngularJS front end. AngularJS is one of the very popular front end libraries for mobile app, for web services. As mobile web services, it can do both. The two main ones that I know are AngularJS and React.js. So here already from Zeppelin, you can also program your AngularJS. Like your friends, maybe you have some friends from CIS, they are quite familiar with app programming. You tell them Angular or React.js, you tell them AngularJS. If they can give you some code, you can actually run that code. You can see the front-end visualization in Zeppelin platform. And this reinforced my point, Zeppelin is not a compiler. It's not an interpreter. It's just a fancy tool that you can write code, and when you press the plus button, it will send it to the compiler and interpreter at the back end. It just combines that all for you. What makes Zeppelin nice is you don't have to install this on your hardware. You can just put it on a container. And when we say put it on a container, you save this container, you can open this container anywhere else. You don't have to actually do the hard work of, oh, I need to do an installation and all that. I don't know how many of you still do that, because I think many of the apps nowadays are all browser-based. So maybe you've not gone through that pain of having to install software from scratch, like you have to open the CD and all that, because your laptops don't come with CD anymore. You just download it. But if you have actually downloaded any kind of like executable software from Windows and all that, you have to log into the root mode. Then there's the Microsoft installer. Yeah, that was the old days. Like every single software we write, or even any library, you have to install it that way, right? What is installation? It is just storing these instructions somewhere on your hard drive. And then when you click the executable, it's just loading that binary instructions directly to your processor. So Roy, let me summarize your question. Why filter exists in Spark doesn't exist in R? Because filter is just one way for you to perform the operation, the MapReduce operation I was describing this morning. Spark cannot do it that way. R cannot do it that way, because Spark is doing a fundamentally different way of approaching programming. R, if you want to do the filter, you actually have to look at your data frame. You check one by one. You have to write a loop to check one by one each row. Where is para? And if it's para there, you save it. If para not there, you remove that row. You have to write the code one by one, line by line in R in order to do that. There is no one-line function to do that. If there is, it is still probably doing it line by line, have to check one by one, because it is not using the MapReduce programming model. MapReduce, the idea is that I just break up this data, and then there's a way of actually computing it, the same instructions on each data type. That's why the filter in Spark does not exist in R. You cannot expect that just because there's one a function call in one framework, it will exist in the other. The job as a programmer, as a coder, is you have to double check. This is why when you choose your language or when you choose your framework, there are two different things. Language, you choose, you have to check what libraries are available for you. You choose language based on, first, the quality of libraries that can support your work. And then you also choose it in terms of its execution speed, what is the compute overhead of the framework, and the back end, the interpreter, right? And once you choose, it's not so easy to switch back because you're using a lot of these libraries, and you need to, if you want to change, let's say you write some code in Python, you want to change in R, the first step you have to do is you have to check all the libraries, that function calls you're using in Python, do they exist in R? And I can tell you, there's no guarantee whatsoever they will exist in R. And if they do, there's no guarantee it'll be the same name. And if it's not even the same name, there's no guarantee you'll even take in data in the same format. And that's what makes it a pain, right? So don't come in with the expectation that everything is worked out. The world doesn't work like that, right? It's just that you're just so used to having products that everything is so finished that it has come to become something that's natural. But when you start drilling down to how these things are built, you realize how much of work it actually takes to do this mapping. And then you'll be a bit more careful to check, is this operations here? This is why I'm trying to introduce you to all these different tools, is to actually let you hit, this is really a real problem in industry. You cannot just say, I pick Python because of that, or I pick MATLAB, right? MATLAB, one key problem with MATLAB is you have to pay a lot. And the backend engine, I don't know how useful that is compared to Python, right? And it's great for computing and all that, but it's got its own challenges lah. Like I mean, it can have GUI and all that, but it's a bit more clunky than some of these web-based REST API stuff lah. Yeah. Okay. And then the second question is why the R libraries not in Zeppelin? Is because the Zeppelin, is because the R interpreter on the virtual container in Docker is not set up properly. We did not set up the compilation, the GCC compilation. The interpreter is okay, but when you load the library, the interpreter will call the compiler. The compiler is not set up properly, so it cannot install some of these instructions because the installation requires you to compile, to convert the instructions to binary form. And that's what's failing in this particular Docker version of Zeppelin. So if you really want to see that work, bypass Docker, install RStudio directly on your laptop. You use the traditional way of actually loading the libraries, and hopefully your laptop is set up to do the compilation. If your laptop is not set up to do the compilation, you're going to have the same problem. You're going to have to install local compilers lah. So if it's Microsoft Windows, it's a little bit more challenging lah. But the nice thing about Microsoft Windows is maybe most of the libraries are already pre-compiled binaries. This is what we call binaries lah. Binaries means they have already been translated into the binary form of the instruction. So you're just saving them up and it will just work lah because it doesn't need the compilation step. So Roy, I hope that explain in more depth why these challenges are there. Do you follow it, or is there something I can clarify further?
I understand.
Okay, all right.
Thank you, sir.
Sure. So it's good. It's a good question because I think one of the things that I've been hoping more for the computer engineering is you ask a lot of these questions lah, because these are all things that go on under the hood. You don't see them. And most people actually will say, oh, programming is difficult, programming is difficult. Programming is not difficult. The algorithm is difficult, not the programming. The programming is you're just spitting words. It's like people say that speaking English or speaking Bahasa Melayu or speaking Mandarin is difficult. No, it's not. If you know the vocabulary is not difficult, what's difficult is what are you going to say, right? That's what's difficult, right? When people say, I have a speaking problem, I cannot speak in public. It's not because they don't have the words, it's because they don't know what to say, right? If you know what to say, over time, you'll be able to get the words. Programming is the same. What to say, that means, what do you do first? Do you filter out for para? Then do you split the lines? Then do you do addition? This is the algorithm. It is the intelligence of the program. It is the sequence of steps to achieve the data collection that you want. That algorithm is difficult. That is the one that I'm trying to train you to write. The syntax, whether you're using line contains, this is easy. You just look up the book. It's all here. The difficult thing is, if I give you a problem, I said, can you tell me, for example, from this vaccine, okay, can you tell me something like, which is the most popular vaccine combination in Malaysia? There is no book anywhere that will tell you how to do it. Because you have to figure out the algorithm. You say, okay, I got this raw data, I have to figure out which is the most popular vaccine. So you have to start to think, what are the steps I actually need to do? I have the daily vaccine groups from each location. So if I want to get the most popular, I probably will have to sum up all of them over time and over all the districts. And then I find the combination that has the maximum. So that is an algorithm. The first step is I have to get every column here. I have to add all of them column wise. Then I have to compare these columns, the sum of this column with the sum of this column, the sum of this column, the sum of the column to find the maximum. How do I do that in the program? That is an algorithm. That is not programming. That is algorithm, because you can write the pseudocode for this without any syntax. And conversely, if I give you the pseudocode, you actually don't need to think. You can just write it in Python or MATLAB in 15 minutes because you're just translating. What's difficult is the algorithm. That's where most of you get stuck, because that's the part that you actually have to think step by step. So for example, just now, how would I actually do it in a map reduce process? Well, first, if I have the map for all of these, maybe what I need to do is I need to actually have key value pairs lah. I need to break this up. I will have the key AAA and the value each of these. Do I need to know the districts? Do I need to know the state? No, I can throw away the information because I want to know for all of Malaysia, right? So I have a key value. So I have basic data pairs as AAA 0. That's for Batu Pahat, but I don't want to store Batu Pahat. Then AAA 0. So I've got all these key value data pairs. Then for all the AAA ones, I just take the sum. For all the AAC one, I take the sum. For all the AAH ones, I take the sum. For all the AAP ones, I take the sum. So this is a map operation, a reduce operation on the AAC key value pairs. And then I will just do a comparison, a reduce operation comparison for all of that. So this one is the key value pair approach. I will teach it to you the next round, the next session we have next week, right? So that is the difficult part, the algorithm part. So unfortunately, the only way I know how to teach you the algorithm part is by giving you assignment to force you to do it. Okay, because I can tell you the algorithm for one particular task. Today I've already told you the algorithm for how to actually find the maximum, the most popular one, right? But tomorrow maybe it's not vaccines. Tomorrow maybe they want to see which one has the fastest trend, rising fastest trend. So there's no way that any university can teach you all the possible algorithms that you need to develop in your entire life. There's no way. What we have to teach you is how to develop those algorithms in a way that it will work. And the only way I can do that, traditionally, the way programming is taught is they teach you syntax. They teach you, these are all the tools, you go figure it out. I'm trying to simplify this process by actually reducing the number of kind of tools so that you can actually focus on how you want to juggle and combine the data and generate the algorithm. But you can't get there until you familiarize with what these things can do and you start going to think in the map-reduce way of programming. And that's what chapter 2 of this book does. Chapter 2 of this book has given you 3 examples going into great detail how to write how to split the data up for 3 different applications: matrix multiplication, word counting in a text, okay, and the database operations, logical operations join and all that. There are 3 very different applications. It's giving you a very detailed way of actually splitting that up, and you can actually take that and actually use that to write Apache Spark kind of commands But it's a process. Maybe the first step is you start with this. I'll give you a simpler assignment so that you can familiarize with the transformation operation and the action operations. So that will be assignment 2. Then next week we'll go into key value pairs, probably another assignment just on using the key value pair approach for data analytics. And then we have one final assignment where you just combine all of that with the visualization. How does that sound to you? Too much work, too little work? Okay.
Yes, okay.
Okay, yeah. All right. So you let me know because it really depends on how fast you can get the visualization. I mean, we already delayed by 2 weeks already, the visualization, but it should be due on Monday. And the visualization actually the simplest part because most of the difficulty is for you to set up the platform and get used to coding because I think most of you don't have enough coding practice. That's why you don't know how to read files and all these kind of things So it's to get you very quickly up to speed on that and that you set up your platform on your PC. If you've not done that, I'm sorry but you're very, very late it's 1.5 months already, and it's kind of impossible that you've not done anything for lab 1 in 1.5 months then you might as well not register for this course and take it later, lah, save your money kind of thing, But if you can still catch up, please do catch up, lah, because beyond this point, if you still have problem with Docker and you've not solved it, or you've not asked for help, you're going to be falling very far behind, lah, right? So I hope all of you have that, and we'll submit the visualization by this Monday. That will be good, because that tells me visualization okay. You can actually replicate code. You can actually do some simple thinking, algorithmic thinking, what you want to show and how to actually extract and show the data. That is actually the goal of assignment 1. Assignment 2, the goal will be to familiarize you with the transformation and actions. I'll give you some filtering operations and all these things, ask you to generate some numbers, simple numbers and all that. It's just to get you into this map-reduce programming mode. Then the key value pairs is where we actually do some more intensive data analytics. Okay. And then let's see, if we end at assignment 3 is also okay, depending on your speed. If you actually want to see everything glued together, the best will be to show you assignment 4, which is you do the analytics for key value pair, you link it up with the visualization. And there is a way to do it in Spark. You can actually pass, in Zeppelin, you can actually pass whatever results from Apache Spark, you can pass it to R. Okay. And Roy, just to, as a final parting word, Roy, before, just to give you a bigger picture of everything, but if you don't get this, it's okay. R has been optimized to run in Spark. Okay, there is a version of R now that all the R commands, or most of them, can be implemented as MapReduce control flow programming, MapReduce data flow programming. So that is where you see Spark.R interpreter. Spark.R interpreter is still an R interpreter, but all the R libraries are now implemented as MapReduce operations. Okay, so I didn't want to confuse you earlier on, because earlier on I was trying to give you that understanding of compilers, linkers, loaders, assembler that is compiled to a specific binary instruction for a specific processor. And I want to also give you the understanding of what an interpreter or translator is, which is you compile to an intermediate, like a general purpose format, and then there's another step of a translator that will directly translate it in real time to the binary instruction. And that is for control flow. It's also for Spark framework, but that's a traditional programming. Our traditional users did that, but somebody and a group of people, open source, have already gone in and done some hard work. Some of the R libraries have already been modified, so they are implemented, they're executing as MapReduce operation, and that is Spark R. But the issue here is, now that you understand there are two different ways of programming and everything has to be written, has to be ultimately converted into binary code. The issue is for Spark R, I don't know which functions have been made into Spark compatible and which functions has not. So if you're running Spark R, you can still use the R functions, but you know that they're running underlying on Spark. But I'm not sure which libraries are compatible, which libraries are not. You have to explore that. That's more like exploration. And over time, it will change. As Spark R becomes more popular, more and more people will write the translation of the R functions to Spark implementation. Okay, Roy? So that's now closing everything to share Spark and R. They're different. They're not the same. That's why if you think about Spark as a programming language, then I tell you Spark R, you're like, oh shit, what is that? Right? But now I'm trying to explain to you, Spark is not a programming language. It is a programming framework. It is a way of writing programs. The language that I can use to write Spark is Java. I can use to write Scala. I can use to write Python. And now I can also use to write R. I can use R syntax. That means the words, the language of R. I can use Java syntax, the words, the language of Java. I can use Python syntax, the words, the language of Python, or I can use Scala syntax, the words, the language of Scala. But the underlying compilation interpretation, Spark engine. Okay. And if I'm doing it on traditional Python language, the underlying conversion is Python interpreter. Okay. Can, huh?
Yes.
Okay. That's all I have actually. So I'm going to share this on YouLearn today. So just get started, and within the next few days, I will put up assignment 2. with the anticipation that you're all finishing assignment 1 already. I'm going to wait for another couple of minutes. If you have any questions that I can further clarify, don't be ashamed. Everybody is learning. The more questions you ask, the better I can share with you all these things that are going on under the hood. Okay. No questions. Okay, thanks Roy. Thanks for feedback. So Arina also gave some feedback about an hour ago. Maybe the rest of you, if you can just type something on the chat box. If I see a lot of no questions, then we can end the session today. If not, I will just wait a bit more because today's material is a little heavy because it is new. But I really believe this is worth it. I mean, one thing you can do is you can actually do Spark Jobs Malaysia. Cognizant, looking for Spark Scalar developer. Software engineer, how to DXX technology. EBDES Malaysia, Apache Spark developer. This one is not lah. Senior software engineer, Monster, DXC technology. ANK technology, Spark developer. DOX, Databricks, Apache Spark. Databricks is a online version of it lah. Data engineer for Agoda, Apache Spark. Apache Spark developer, senior data engineer. This is not Spark SQL for ByteDance. ByteDance is also looking for Spark developers. So you do something like this, you can actually see full stack developer. This one full stack is web, it's not for Spark. So I don't know, sometimes they will tell you the Hadoop developer, Tata consultancy. Sometimes they'll tell you the pay, sometimes they don't. This is just to encourage you to see that the things that you are looking at is very relevant. There is demand for this. The demand is growing quite rapidly actually, because for all these big, data engineer, 5K to 9K per month. PPG, what is the requirements? Data ingestion, pipeline, SQL, Oracle, Azure Data Lake, Data Factory. This one is more tied to back-end cloud. This is platform administrator. See, banks as well have requirements for data engineers. But this one, for example, you see Apache Spark is 8 to 9K, kind of the way. So you have these candidates, bachelor's degree will be there. You know how to use this software. Yeah, but the thing here is funny, they are giving you just a kind of generic explanation, but from the title itself already they're telling you have to use Apache Spark on the Databricks framework. Yeah. So this is just to motivate you why this is chosen, why I'm pushing you to learn all this, even though it's making you it's making you a bit uncomfortable, I know, because it's something that's very new, transition Hadoop and develop Hadoop techniques, like all of this. So this is part of MapReduce. That Hadoop Spark. Actually, it's not Hadoop Spark. We sometimes just by looking at the advertisement, you know how much the company knows about this or not. They're relying on a lot of tools, Azure. Yeah. Okay. All right. So I was just trying to wait for time if there are any questions. No questions. Okay. So in that case, then happy exploring. I'll share this on ULearn, and I'll see you again next week. Okay. All right. Bye-bye.
Thank you, sir.